Hello, my name is Will Miller, and we're going to go over producing electric current. Our objectives for this is what is electromagnetic induction, what is the difference between alternating current, direct current, and how does a transformer change the voltage of an alternating current. So the very first thing you need to understand is who discovered this? Well, electromagnetic induction was really discovered by Michael Faraday and Joseph Henry about the same time in the United States. So what is electromagnetic induction? Well, electromagnetic induction is the generation of a current by changing a magnetic field. So let me show you what that's like. Okay, so here we have a bar magnet, and here we have a wire around an iron core hooked up to a light bulb. So what we're going to do is we're going to rotate this magnet, and you're going to see the positive charges moving back and forth, and the light bulb is starting to pulse. Well, remember, light bulbs don't care if it's AC or DC, so it's going to pulse no matter which way the current is traveling. But the important thing here is what's making it pulse. Well, what's making it pulse is the magnetic field is pulling the charges back and forth, because it's like remember, these electric charges act like little small magnets. And of course, you can move one magnet with the other. So as the magnets pass by one another, as the magnet passes by, it pulls on the charge a little bit and causes it to change, or produces a magnetic force on it. So let's go back and let's learn a little bit more. So again, Michael Faraday and Henry found this out about the same time. And I have a thing for Michael Faraday. I think he's a cool dude. I think that he, as you've watched Einstein's Big Idea, you've seen where, Sir Humphrey Davy gave him a chance. And Sir Humphrey Davy was an astoundingly great scientist in and of his own um, abilities. But, it's said that the greatest thing he found was Michael Faraday, and that's because what Michael Faraday provided for humanities, which was this electromagnetic induction, and really diving into how it works and how a magnetic field can cause an electric current to flow in a wire. And of course, what's cool about this is that they actually gave Faraday, it's such a big thing that they gave Faraday his very own unit. The farad is a unit of capacitance, or of ability to store charge. And actually, Henry got um, his own unit. A Henry is the ability to store current. And of course, what's interesting is that, of course, this is acting like this stores charge, which is called a capacitor, and an inductor is just a winding, stores current. So it's a way to help even out the flow of charge and current at the same time, whenever you're starting to talk about alternating currents. And we'll talk more about that as we go through, but it's a big deal in electricity, knowing how to work with these two devices. Okay, so let's talk a little bit about generators. A generator uses an electromagnetic induction to transform mechanical energy into electrical energy. So how does it do this? Well, you guys can write this down in your notes, and I'm going to give you a second or two to do this, but then I want to show you what this looks like. So in a generator, as the coil keeps rotating, the current that is produced periodically changes direction. Now, some people would argue whether or not this is a generator or an alternator. And what we really want to do is we want to use a very generic term. What you're seeing here is an alternator, but a generator can actually do both. A generator it just generates current. It doesn't matter what direction it's going. If it's alternating, though, more specifically, it's called an alternator. So that's what's in your car normally if it's a newer car. If it's an old car, we just call it a generator, because it actually is not producing an alternating current. It's just producing a direct current. So let's look at what that looks like. So just like with the other setup, you know that whenever you have a wire that's moving through a magnetic field, earlier we saw that the magnet was doing the movement. Now we're keeping the magnets stable, and we're moving the wire through the magnetic field, but still yet you have charges that get pulled on from this magnetic field. So as you can see, it's pumping the electrons, and that's really a bad term, but that's the way you can think of it. It's pulling the electrons. There's a magnetic force, and it's pulling the electrons back and forth through this circuit. So let me slow it down a little bit. And you can see it's pulling on these electrons as it swipes back and forth through the circuit. And of course, the faster you go, the more current's going to be able to flow. So let's take a look at this on the oscilloscope. An oscilloscope just reads the wave functions that's being produced. So I'm going to slowly go through it, and you can start to see there's a wave, like a water wave. And we'll talk more about waves in a chapter or so. But right now you can see a small wave, and I'm going to increase the rotation. And as you can see, that increases how often the wave is occurring. So this is just plotting out the back and forth motion of the charges or the current in this wire over time. Okay, so we know that we get electricity in our home, but how does it get there? Well, generally speaking, if you're not talking about solar, then you're probably talking about either nuclear or coal-fired plants or oil or natural gas or some sort of fossil fuel. Now, there are a few plants that's actually fired through solar means. They heat up some molten salt, and that allows it to heat up water. Regardless, generally, at some point, there's steam being produced somewhere, and that steam then expands and causes these turbine blades to turn, therefore turning the generator, which I just showed you basically how it works and rotating it. So it takes this mechanical energy. Actually, it started out as thermal energy, and it creates mechanical energy, and then the mechanical energy creates electrical energy. Okay, so we haven't mentioned wind, but we need to mention wind. Wind just basically, gets rid of the conversion from thermal to mechanical, and it just goes straight from mechanical to electrical. It hooks up a giant windmill. You've seen these. Probably if you've ever driven out in West Texas, you've seen a lot of them. And the reason why is because Texas sits right in a very, very windy region. If you see this, this is like, it shows you the amount of wind in this area. It's a lot more in this area than in other areas of the United States. In fact, Texas is the #1 wind generation state in the U.S., followed by Iowa and Oklahoma. And you've seen this before. In fact, I just showed you a little bit of the alternating current and how it's produced. So alternating current just means it's going from positive to negative to positive to negative. Whereas direct current, that's like what batteries have. And it's always direct, like plus 1.5 volts or plus 10 volts. So current's only moving in one direction with direct current, whereas alternating current, it goes back and forth. So what I want to show you here is what happens whenever I change this magnetic field between the coils. They're not physically touching, but this is causing this to light up, and there's no physical change between the two or touch between the two. And how is that working? Well, remember that anytime, just like with the generator, if you change the magnetic field, that's going to cause a magnetic force on these charges, right? It's causing them to move. So, and of course, this is creating a magnetic field because you have moving charges, which are like little moving magnets. So what would happen if we were able to change that magnetic field? Look at that, even by just changing the voltage. What if I was able to change the magnetic field just by having this on here? Just by changing the current. So right now I'm changing the current now. So if you notice, these are flipping back and forth. So it's creating voltage here without moving this and without moving this. In fact, if I put it inside it, look what happens. So this is the basics behind how transformers work. It takes a little bit of an electric motor and a little bit of an electric generator, and it kind of brings them together. It's everything that we've talked about brought together. So you have a coil that's inducing a current through a magnetic field into another coil, which is kind of cool. So that's what this is all about right here. We have a transformer. That's what transformers do. And these are just devices that can increase or decrease voltages of an alternating current. And it turns out the math on this is just astounding. And I'll let you guys read through, the rest of it. I'll let you guys write through the rest of it. But I want you to look at this math. 60 volts in with a primary coil of 10 turns. 120 volts out with a primary coil of 20 turns. So you get twice the amount of voltage, but notice that you have twice the amount of turns. You should be able to see the math there. If this would have been, say, 5 turns, and this is 20, then you would have had 240 volts out because it would have been quadrupling the number of turns. And likewise, if this would have been 10 and this would have been 10, it would have been 60 volts in and 60 volts out. Notice there's no physical wire that's touching between these two areas. It's basically using this as an iron core magnet between the two coils. So this is, I've talked about it since we've been talking about electricity, how Westinghouse originally took the electricity that was being produced at Niagara Falls and brought it all the way down to the World's Fair in New York City and lit it up. And this is what finally put the coffin nail into Edison's idea that he was going to light up the world, produce electrical energy for all of the world using direct current. Whenever everybody saw just how far Westinghouse could take energy and move it, it was over. It was game over. Westinghouse won. Okay, so transformers have an input voltage. We just saw this, an output voltage. The input voltage is the primary coil. The output voltage is the secondary coil. So in this case, this is the input voltage, and this is the output voltage. And this is in words only. I mean, really and truly, if we would have put 120 volts in here, we're getting 60 volts out here. And this is one of the things that make hooking up a generator, if it's not done correctly to your house, extremely dangerous to people that work on electrical lines whenever there's power outages, because people will just plug them into the outlet, and it's, number one, it's a great way to get dead, but number two, you're going to hurt somebody else if this happens, because they're out there thinking that the wire that they're working on is not got electricity to it, because they're holding one on, they're trying to feed it up, but in reality, you've got 120 volts coming in here, and you've got 17,000 volts on the other side or whatever, because your primary coil is now what used to be the secondary coil. Okay, so a step-up transformer just transformers that increase the voltage. So the number of wire turns in the secondary coil must be greater than that of the primary coil. And of course, step-down transformers, and this is what you see outside on your pole and stuff like that. These are transformers that decrease the voltage. In other words, it takes it from the 17,000 volts on the wire down to 120, 240, 480 volts, depending on, we normally use 120 to 240 in our house, but occasionally you'll see 480 volts ran at businesses because they have a much bigger use of larger currents or larger amounts of power, maybe for melting and smelting of different metals. So it's a really easy equation. Just output voltage over input voltage equals secondary coil over primary coil. So this is commonly just V out over V in equals N2, the number of turns on the secondary coil, divided by N1. Okay, so here's a problem. A transformer has 150 turns in the primary coil and 50 turns in the secondary coil. If the input voltage is 17 volts, what is the output voltage? Well, write down everything we know. We know that the input voltage is 12 volts. The primary coil is 150. The secondary coil is 50 turns. So what's the output voltage? Well, use the equation V out over V in equals N2 over N1. So solve for V out. Well, you're going to multiply both sides by V in because it's on the bottom over here. So you get V in times N2 over N1, and then plug the numbers in, and you get 4 volts out. So does this make sense? Well, yeah, you have more coils on your primary coil than your secondary coil, so it makes sense that it would be a lower voltage. And this is done all the time, like with smartphones and stuff like that. They have to have a much smaller voltage in order to run your smartphones. And by the way, your smartphones run not on AC but DC, but you still have to bring it down from 120 volts down to 5 volts. And that's done through transformers. And then it takes from AC to DC. They use capacitors and inductors and diodes. And diodes we haven't talked about, but it basically just allows current to flow in one direction. So it helps take that alternating current and make it into direct current. So we've talked about power is equal to voltage times current and why we um, always transmit power, electrical power, at such high voltage. Well, the reason why we do that is because it decreases the amount of current. The less current, the less heating of the lines. It also has to deal with how big or round the wires are. If we have a smaller current, you don't need to have a big wire. So it decreases the amount of cost that electric companies have to fork out. Um, and of course, I found these two graphics really cool. This one kind of shows you, I don't know if you've ever noticed, but they have these little things at the top, and you can actually see what voltage a line is by how many these little insulator discs it has. So this one has 1, 2, 3, 4, 5, about 10. So this one's running about 161,000 volts, somewhere in that neighborhood. So the big tall ones, and I live down near Burleson, and if you go further south than this, they actually construct these. And I've seen one of these big ones. They have it just up there all the time. I think they use it to train, but I don't know. But these are the ones that run 450 to 735,000 volts, and they might have one or two that span to the north, one or two that spans to the south, and they carry a lot of power. And they're extremely tall. And then of course it just goes all the way down. These are the I have. There's some of these that run about half a mile away from my house, and that's the ones that run it all the way to Southwest Fort Worth. They power all of Southwest Fort Worth, which is kind of cool. And then you get these that run whole neighborhoods. Okay, transmitting and alternating current. All those step-up transformers and step-down transformers change the voltage at which electrical energy is transmitted. They do not change the amount of electrical energy transmitted. So, I just talked about this. The energy, the power is still the same. It's just the current that has changed, right? So the essential questions you should be able to answer. What is electromagnetic induction? What is the difference between alternating current and direct current? And how does a transformer change the voltage of an alternating current? Okay, have a good day. Thanks.